Hello everyone. Uh, in the previous lecture, we've been discussing this at least a bit about this. Just give me a moment. Yeah, at least a bit about this left cosets and right cosets and so on. Yeah, so because one of the reasons for doing that is that we'd like to still continue the discussion of the notion of cosets, and that will lead us to one of the important notions in the theory of groups. There is a notion of quotient groups and so on. Okay, which you will learn in a moment. Okay, or in just in next the next few lectures will be about the notion of quotient groups. Okay, yeah. So, and also we revisited the Lagrange's theorem, more specifically the proof of the Lagrange's theorem, which states that if we start with a finite group G, where is it? Yeah, it's mentioned here. If we start with a finite group G, and then we take a subgroup H of this group G, and then we look at the index of the subgroup H in G, that is, we look at the number of distinct left cosets or the number of distinct right cosets. It doesn't really matter, because by lemma 181 the number of left cosets is equal to the number of right cosets. So if you look at this index, which by definition is the number of distinct left cosets, okay, and by this lemma, this is by this lemma, this is also equal to the number of distinct right cosets of H in G. So this number multiplied by the order of H is equal to the order of G. So this is what we obtained in the course of the proof of Lagrange's theorem. Okay. In fact, this was the statement that he proved, and then it followed that that this has to be an integer. In other words, the order of a subgroup divides the order of a group when the ambient group G is finite. Okay, yeah. So let's continue along that line. So for instance, here is one of the here is one of the, how do you say, important uh, results or important facts that we may use and we will be using. I mean that one may use at any time without referring to a proof of this statement. Of course, not at a time when you are asked to prove this statement. Okay, yeah. So it says that if you start with a subgroup H of a group G, and so if you start with a subgroup, if you start with a subgroup, so if you start with a group, just give me a moment. So I'm just not able to select it appropriately. Okay, so if you start with a subgroup H of a group G, and then we assume that this has got index 2 in G, then it follows that this subgroup is normal. Okay, so usually one writes that a subgroup of, or any subgroup of index 2 is normal. Okay, so let's try to prove this, or maybe before getting into the proof, it would be a good idea to recall the definition of a normal subgroup, right? uh, yeah. So suppose, or rather, so let's recall that, uh, just give me a moment. Yeah, okay, I've already started the recording. uh, Subgroup H of a group G is said to be normal if what, if G H G inverse lies inside H for all H in H and G in G. Okay, yeah. uh, okay, so let's look at some of the cosets of this subgroup, and that from that consideration it will follow, that this property holds. Okay, so we start with a subgroup H of G of index 2, and then we pick an element little g of G. Okay, so if you pick an element little g of G, it's important to first focus on, or maybe it's important to focus on the elements G of G that lies outside H. Why? Because if you need to prove that for G lying within H, okay, so if you'd like to prove this containment for G lying inside H, then it is trivial, right? Because if G lies inside H, and then of course you're taking the element little h from H, so this element lies here, this element G lies in H, This element also lies in H. This element also lies in H. And H being a subgroup has to contain the product of any of its elements. Okay, maybe two elements, three elements, and so on. Okay, so if you take this element little g from H, then this containment is immediate. Okay, so let's start with an element little g of G that lies outside H. Okay, so now we consider the left cosets GH and H. H is certainly a left coset, right? Because H is equal to the identity element times H. Okay, so if you look at the left cosets GH and H of the subgroup H, then they have to be disjoint. Why is that the case? Because if they are not disjoint, then they are equal, right? Because you know that any two left cosets, they are either equal or disjoint. So if they are not disjoint, then they have to be equal, right? Then you know that the element little, then you know that the element little g lies inside gh. So it will follow that, when gh is equal to h, it will follow that the element little g is an element of this subgroup H. But that is not the case by the choice of this element little g. Okay, great. So these two left cosets of H, they are disjoint. On the other hand, we have started with the hypothesis that H is a subgroup of G of index 2. So there are exactly two distinct left cosets. Okay. So since we have found two disjoint left cosets, it follows that they are distinct, and so G being the union of two distinct left cosets. So these two left cosets has to be those left cosets, right? Okay, so this G is the union of the left cosets GH and H. Okay, now if we look at the right cosets AG and H, note that H is a right coset of H because H is equal to H times the identity element E. Okay, so if you look at these two right cosets of H, then they are disjoint. Okay, and we know that two right cosets of a subgroup, they are either disjoint or either disjoint, and otherwise when they intersect, they have to be equal. So they are either equal or disjoint. So since they are disjoint, and we know that this subgroup H has got index 2 inside this group G. So this G, the group G, can be expressed as a union of two right cosets, and you have already found right cosets which are disjoint, and hence they are distinct. So it follows that G is equal to the union of these two right cosets. Okay, and now we know that the intersection of these two left cosets, that is empty. The intersection of these two right cosets is also empty. Okay, so then it follows that GH is AG, because this group G or this set G is the union of these two, right? These two subsets, that is also equal to the union of these two subsets. Okay, so in other words, if you start with this subgroup H, then along with H, if you take GH, then you get this full group G, and along with H, you can also take this subset HG, then you will also get this full group G. Okay, and now H has no intersection with this subgroup, right? And H has no intersection with this coset, right? And H has no intersection with this right coset either. Okay, so it follows that GH is same as HG for any element G inside the group G that lies outside H. Okay, and now if you take an element G prime from H, it follows that G prime H is HG prime, right? Because both of them are equal to the subgroup H. Okay, so it follows that G inverse is equal to H. Okay, and this is precisely what we have been looking for, right? If GH, so you know that G inverse is equal to H, so the element little g, little h, little g inverse that lies inside H, right? For all H in H and for all G in G. Okay, so this is what we have been looking for, and we have established that H is normal in G. Okay, great. So now let's continue along. Continue along. Okay, so let me read the very first sentence of this exercise, then I will be able to complete this sentence. So we start with the group G of order 2p, where p is an odd prime. So just to ask you a few questions, or maybe to remind you, we already know several, at least two examples, not several, they're not much examples. We already know two examples of such groups. Okay, sorry. For the very first instance instance is that Z mod 2pz, and the second instance is that what? Is a dihedral group of order 2p. You can also say that there is a third instance, right? You can look at the group of 2p power order, sorry, 2p power, this 2pth roots of unity. So there is mu 2p, okay? But just give me a moment. Yeah, but these two examples, I mean, although they appear to be distinct, in fact they are distinct, but you do not consider them different in the sense that these two are isomorphic. Okay, just these two. Okay, maybe this looks bad. Maybe just these two are isomorphic. Okay. Okay, great. So actually we are continuing along the lines of dihedral groups. Okay, so we have already been studying dihedral groups for the last few lectures, and we are still somewhere around the dihedral groups right now. Okay, although we are not going to kind of use that, I mean, use information coming from the dihedral group, but let's see what we can study or what we can do. So we start with a group G of order 2p, where we take p to be a naught prime. Then this exercise states asks to prove that the group G contains an element of order p and an element of order 2. Right? This is sorry. Just give me a moment. Okay, great. Yeah, so then we need to show that this contains an element of order p and an element of order 2. Okay. Uh, okay, so let's try to just focus on the main examples just to convince ourselves that this is the case. Okay, this is only to convince ourselves, or probably to explain, sorry, or probably to explain this exercise, or probably to convince ourselves or maybe yourself to convince that this can indeed be so. Okay, of course we need a proof. By studying these two cases, that will not lead us to a proof. Okay, unless we prove something else. Anyway, uh, so let's look at the group Z mod 2pz, and if you look at the element 2 more precisely, the mod 2p congruence class of 2, so I should write 2 bar, and if you look at the element p bar, then this is an element of Z mod 2pz of order p that one can show, and this is an element of Z mod 2pz of order 2. And now if you look at the dihedral group d, oops, there is no z here. If you look at the dihedral group d2pz, and there if you look at the element r and s, then as you know by now that this is an element of the dihedral group of order p, and this is an element of the dihedral group of order 2. Okay, so the examples of groups of order 2p that you know so far, that have, I mean, these examples have this property that such groups contains at least one element of order p and at least one element of order 2. Okay, yeah, so here when I say that an element of order p, I'm not saying that it contains exactly one element. Okay, so please be careful with this kind of sentences. So I'm saying that it contains an element of order p. It contains even more. In fact, it does contain a lot more than this. Okay, anyway, so let's see what can we do in this case. Okay, or how one may proceed to prove this statement. Yeah, so it seems that it is easier to prove that it contains an element of order p. Okay, and to do so we proceed via the method of contradiction. So we first assume that G contains no element of order p. Okay, then if you look at any non-trivial element of G, okay, just give me a moment. Okay, just give me a moment. I think there is somewhat, okay, so there is some trouble with this sentence that any non-trivial element of G has order 2. No, cannot do that. Okay, yeah, but still there is a way to bypass. Just give me a moment. So current template, and then rotate this page. Yeah, oops. Yeah, so we start with a group G of order 2p, and we assume that it contains no element of order p. Okay, And now if you pick an element G from G, and if we assume that G is not the identity, then what are the possibilities for the order of G? So you know that order of G is equal to the order of the subgroup of the group capital G generated by G, and by Lagrange's theorem this divides the order of G. So this is by Lagrange's theorem. Okay, and then what are the possibilities for this order? Okay, yep, so it could be 1, it could be 1, or it could be 2, or it could be P, or it could be 2P, right? And it is not possible that this is 1 because you have started with an element of order E. Okay, and here you have assumed that G contains no element of order P, so this is not possible either. So what we are left with are just these two possibilities. Okay, if G contains an element of order 2P, but if G contains an element of order 2P, then what? I mean, if G contains, I mean, okay, if this element little g has got order 2P, then one can show if order of this element G is equal to 2P, then one can show that then one can show that the order of the element G square, sorry for this bad handwriting, the order of the element G square, that is equal to P. But again, that is not possible because you have started with the hypothesis that G contains no element of order P. Okay, so what you see is that even this is not a possibility, that this element little g has got order equal to 2P. So what we are left with, that order of this element little g is equal to 2. Okay, so okay, as I was saying that there is some trouble. No, I mean there is no trouble, but there is some gap in the sense that the argument was not detailed. Okay, and this being a introduction to this notion of groups, so we cannot leave any gaps. Okay, or we cannot kind of leave the details for the reader or for anyone. Anyway, so then as we have just established that any non-trivial element of G has got order 2. Okay, and this certainly implies that G is abelian. This is by one of the exercises that we have solved long back, I think at the very beginning. Okay, and now if you take just take two non-identity elements, two distinct non-identity, okay, maybe we should write two distinct, otherwise it will not work. For any two distinct, so now if you take two distinct non-identity elements x5 from G, then this subset forms a subgroup of G of order 4, that one can show from these two statements that any non-trivial element of G has order 2. Okay, and that G is abelian. Okay, great. Okay, so now by Lagrange's theorem we know that the order of a subgroup has to divide the order of a group. So we just so applying to the specific subgroup, we see that 4 divides 2P, but P is an odd prime, so this is not possible. Okay, so our hypothesis that G contains no element of order P is not valid. Okay, so you have established that G has to contain an element of order P by the method of contradiction. Now it's remaining to show that G has to contain an element of order 2. Okay, again you will show this by the method of contradiction, and we will begin with the hypothesis that G contains no element of order 2. Okay, we're going to assume that G contains no element of order 2. So of course it follows that G cannot have a subgroup of order 2, because if it has a subgroup of order 2, then the non-identity element of such subgroup has to be an element of order 2. Okay, so now if we apply Lagrange's theorem, we see that if you take any subgroup of G other than these two, this subgroup G and this subgroup, this trivial subgroup containing the identity element, so any subgroup of G other than these two, okay, so other than these two has to be of order P. Okay, because you have assumed that G contains no element of order 2. So why that is the case? Any subgroup can have order among these 4 integers, 1 or 2 or P or 2P. Okay, if it is it can have order 1 when this is the if and only if it is this subgroup consisting of the identity element only, it will have order 2P only when it is G. Okay, so the possibilities that are left out is this 2 and P. but you have already observed that from which follows from our hypothesis that G cannot have a subgroup of order 2. Okay, so it follows that any subgroup of G other than these two has to have order P. Okay, and now if you take two subgroups of G of order P, then their intersection is a subgroup of both of them, right? If you take just one more remark, this is something that you have seen in some form. If HK are subgroups of G, then you know that H intersection K is a subgroup of G. It's also true that this is a subgroup of H, and this is also true that this is a subgroup of K. Okay, yeah. Okay, great. So now if you take two subgroups of G of order P and look at their intersection, that is a subgroup of any of those two subgroups. Okay, and such a subgroup being of order P, so that intersection has to be of, the intersection being a subgroup has to have order equal to 1 or order equal to P. It follows from the Lagrange's theorem. Okay, so if you take two subgroups, then they're either equal or their intersection is equal to the identity element, the subset consisting of the identity element. Okay, so now let's speak one identity element X from G. We need, now if you look at the subgroup of G generated by this element X, so you know that this cannot be G, right? Because so why this cannot be G? Okay, it cannot be G because of the following reason. Okay, so if it is of order, if it is equal to G, then you have found an element of order 2p. Okay, so if you have inside a group of order 2p, if you have an element of order 2p, then it follows that it has to have an element of order 2, but that is not the case by our assumption. Okay, okay, great. So now if you start with an ordered element of order of G, then the subgroup of G generated by this element X has to have order P. Now if you pick an element Y of G, okay, that lies outside this subgroup X, note that one can pick such an element Y because this subgroup has got order P and the ambient group has order 2P, which is larger than P. Okay, so one can pick an element Y from this group G that lies outside this subgroup X. Okay, so now if you look at the subgroup Y, the subgroup of G generated by this element Y, then this is not equal to X, right? Because if they were equal, then Y would belong here, but in that, but that is not the case because Y doesn't lie within this subgroup. Okay, so it follows that the intersection of these two subgroups is the identity element. Okay, so their union, so to compute the size of their union, we need to just add the sizes of these two and we need to subtract the size of the intersection, right? So you just add the size of these two, to compute the size of the union, we add the size of these two, which is P plus P, that is 2P, and then you subtract the size of the intersection, okay, because that is being counted twice while you add the size of these two sets. Okay, so this union has got 2P minus the size of this, which is 1, right? So this union of these two subgroups has got exactly 2P minus 1 elements. Okay, now again note that the ambient group G is larger than the union, right? Because the union has got 2P minus 1 elements and the ambient group G has got 2P elements, right? So one can pick an element, in fact there is only one element of G that lies outside this union, so you pick it. Okay, that's denoted by Z. And again note that the subgroup generated by X is different from the subgroups that we have been considering earlier, that is the subgroups of G generated by X and the subgroup of G generated by Y. Okay, so now if you pick any three of them, their intersection has to be just a trivial subgroup. Okay, that is the subset consisting of the identity element only. Okay, so you have found three subsets of this group G. Okay, where if you look at their intersections, then you see that their pairwise intersection, that is just the identity element. Okay, so then this then it follows that their union has got exactly these many elements, which is 3p minus 2. Okay, so inside a group of order 2p, you have found 3p minus 2 elements, but that is not possible because this is larger than 2p. This follows from the hypothesis that p is at least 3. Okay, so you obtain a contradiction, and therefore the statement is false, and it follows that the group G has to contain an element of order 2. Okay, this is what was left to prove, and earlier you already proved that G contains an element of order P. Okay, so this is a nice statement, right? uh, what you know in these what you knew in these two contexts for these two groups of order 2p, it seems that I mean, if you start with any group of order 2p, one can show that it has to contain an element of order p and an element of order 2. Okay, okay, great. Yeah, so now maybe we can move on to this notion of quotient groups. Okay, so before getting into the notion of quotient groups, so let's fix few notations. So if you start with two subsets of a group G, then their product is denoted by A times B, and it's defined to be the subset, a subset of G that consists of products of this form A times B, where A is an element of A and B is an element of B. Okay, here AB is of course A, and then the composition law of G. I mean A star, I mean A circle B or A star B as per the composition law of G. Okay, great. And there are certain conventions to follow. So for instance, if we, or rather not actually conventions, but one can show this, that these are equalities. So if you take these two subsets where H is a subgroup of this group of group G, and this is a singleton subset of G, I'm sorry, then the product of these two subsets, okay, by this definition will consist of little g times elements from H. That is by definition the left cosets, the left coset of the subgroup H corresponding to this element G, right? And similarly H times the singleton subset G is equal to the right coset H times G. Okay, right coset Hg. Okay, yeah. And just one more there is one more convention that is good to introduce at this point. So if you take two singleton subsets G consisting of G1 and G2, and A is a subset of G, then this the singleton set and then A, and then this is denoted by G1 Ag2. Okay, and as of now, you can ask me that this can be interpreted in two different ways. That this is first you take the product of the first two, and then you take the product of the product, and then you take the product of this product and this one. Okay, and of course the other interpretation, as you can see, you first look at the product of the last two, and then you take the product of the first, then you take the product of the first one with the product of the last two that you are obtained. Okay, uh, yeah, well, so as you see that there might be certain how to say the so there is certain there is a little bit room for confusion, but in fact such a confusion doesn't arise. It follows from the fact that the composition law of a group G is associative, right? And in fact we have this equality in greater generality. If you start with three subsets A, B, C of a group G, and then it follows that, yeah, if you get the product of A and B and then take the product with the C, the same as A, take the product of A with the product of B and C. This follows from the information that the composition law of G is associative. Okay, great. So it follows from this associativity property of the group law. Okay, so now let's get into this normal subgroups. So there is an important lemma that would be good to prove. As I have already recalled at the very beginning today, that a subgroup H of a group G is said to be normal if G inverse lies inside H for any G in G and any H in H. Okay, great. So here is an important lemma which says that if you start with a normal subgroup N of a group G, then Gn is same as Ng. Okay, that this left coset of N corresponding to this element G is same as the right coset of N corresponding to this element H for any G in G. Okay, yeah, so let's try to prove this lemma. So we start with an element little g from this group capital G, and we know that since N is a normal subgroup, so it follows that G and G inverse is contained inside N. Okay, so recall that G and G inverse is just this, right? By that I mean that G and G inverse is G. Sorry for this bad handwriting. G and G inverse is this. Okay, So this G and G inverse is contained inside N, okay? And on the other hand, it also follows that G inverse Ng, which is G inverse and then N and then the inverse of G inverse, so it's also contained inside N. Again, it follows from the fact that from the hypothesis that N is normal, okay? So this shows that okay, so you have proved that G and G inverse is contained inside N, and you have proved that G inverse Ng is contained inside N. From this statement, it follows that N is contained inside G and G inverse. So you have proved that G and G inverse is contained inside N, and that N is contained inside G and G inverse. Okay, so N and G and G inverse, they have to be equal. Okay, so you have proved that N is contained inside G and G inverse, and that you have proved that G and G inverse and N, they are contained inside each other. Okay, so they have to be equal, and hence Gn is same as Ng. Okay, and that is what this lemma says. And there is an important how to say how do you this lemma is quite important. This says that if you start with a normal subgroup, then the left coset of N corresponding to this element of G is equal to the right coset of this subgroup N corresponding to this element G. Okay, so Gn is Ng. So this so thanks to this lemma, from now on, while we deal with the cosets of a normal subgroup, there is no reason to explicitly specify whether you are dealing with left cosets or right cosets. Okay, and in most of the cases we will not do so while dealing with the cosets of a normal subgroup. While dealing with the cosets of a normal subgroup, there is no reason to explicitly specify whether you are dealing with the left or right cosets. Okay, so this is just this remark. Okay, yeah, okay, and here is an important proposition which says that product of two cosets of N is a coset of N. Okay, so if you look at the product of A into cosets, so what do you mean product of cosets? This is this is the product. This is so you are referring to the notion of product that you have just introduced a while ago. Okay, so just multiply the elements of A with the elements of B and collect all such products. Whatever subset of G that you obtain is called the product of A and B. Okay, the product of A and B is denoted by A next to B. Okay, A juxtaposed. Okay, great. So you start with two cosets of N. You need to show that product is equal to N. There's a more precise version which says that if you take G1 N and G2N, these two cosets, then the product is equal to the coset corresponding to the element G1 G2. Okay, of course, for this proposition there is an important hypothesis that N is a normal subgroup. Sorry, I just forgot to highlight it at the very beginning while going through this statement, because I was already under this hypothesis. I was already thinking under this hypothesis. So this is a very important hypothesis, and this situation is typical to this kind of situation. When you start with a normal subgroup, then the product of two left cosets is equal to another left coset or another right coset. Okay, so the product of these two left cosets G1n and G2n is equal to the left coset of N, or the the coset of N corresponding to the element G1 times G2. This is not too difficult to prove. Okay, it's straightforward, and it follows from this observation that Gn is Ng when N is a normal subgroup of a group G. Yeah, so you look at G1n and G2n. So G1n is either by either by definition or by just a very very simple observation which you have done at the very beginning, right? That GH is Hg. Okay, GH is this product of these two sets. The first set is a singleton set consisting of the element little g, and the second set is the subgroup H. So one has that G1n times G2n is the product of these two, right? And yeah, and by associativity one knows that one can combine this one with this one, that you have already done here, right? And again by the associativity one can combine this one with this one. So one combines N with G2, so we have this G1 and then N with G2, and N with G2 is Ng2, and Ng2 is G2N by the lemma. Okay, and in this G2N is G2, like curly bracket G2 times N, and then by the associativity this is G1 G2, the singleton set G1 G2 times N and then N. So you have the singleton G1 G2 and then product of N with N. So we are using the associativity of product of subsets to obtain this step. and n times n is equal to n because n is a subgroup. Okay. Yeah, and this is what you require. I mean, it was required to prove, right? That g1n times g2n is the coset of n corresponding to the element g1 g2. Okay. Okay, great. Uh, yeah. So this is an important theorem which again focuses on the normal subgroups. Okay. So you start with the normal subgroup n of a group G, and then this theorem says that the set of cosets of n. Okay. So by that I mean the set of left cosets of n. Okay. So most of the time we will be working with the left cosets. Why? I mean, one can also work with the right cosets, but yeah, at least usually I end up working with the left cosets. Okay, and whenever you're dealing with the normal subgroups, then doesn't really make any difference whether you're dealing with the left cosets or the right ones or the right cosets. So if you take the set of all left cosets of n, then that set forms a group with respect to the product of subsets. Okay, with respect to the product of subsets that you have introduced. Okay, just a while ago. So you know that we have just established in this proposition that if you take the product of two left cosets, we end up obtaining a left coset, right? So if you take two cosets and take their product, then that is a coset of n. Okay. So this composition law that takes two cosets a and b and sends it to their product. Okay, that is well defined on the set of cosets of n. Okay. So on the set of cosets of n, the notion of product, that makes sense. I mean, by that I mean that this notion of product is well defined. Okay, so this composition law makes sense. Okay. Okay, great. And now the associativity of this composition law follows because you have already observed it, and that follows from the associativity law of associativity property of the group law of this group G. Okay, since the product of subsets of G has the associativity property, it follows that this composition law is associative. Okay, and now if you take any coset n, this any coset n of the subgroup n in the group G, then you note that n times this coset e times n, or you could have just denoted it by n. Just to indicate that there is a coset, I wrote en. It's perfectly fine to write n instead of writing en. Okay, so an times n or n times en is same as en times n. Okay, which is same as n. Why that is the case? Because by this previous proposition, yeah, it was a proposition. So by this previous proposition, we know that n times e is equal to a times e and then n, which is n, right? And similarly, en times a is also n, right? So both of them are equal, and then both of them are equal to an. Okay. So anyway, so we are this is probably the fourth property, right? That we need to have this notion of identity. Okay. Within quotes, of course. We still do not know whether there is a group or not, so you cannot talk about the identity element. But as you see that this is the right element to look at, and now if you start with an element of this set, okay, of this set, and the set consists of the cosets of n. So if you take an element, so that is a coset. So if you take this an, then an multiplied with a inverse n, or if you take a inverse n and multiplied with n, you end up getting en. Okay. So we see that the set of cosets of n with respect to this notion of products satisfy all the criteria, satisfy all the defining criterions to be a group. So we conclude that this is a group with respect to product of subsets. Okay. Now this is the right time to introduce what we have been talking about, or rather kind of what I indicated in the very beginning of this lecture, that you will be learning the notion of quotient groups very soon. And in fact, the following definition says that you have already learned it. Okay, because this is just this. Okay, if you start with a normal subgroup n of G, then the set of cosets of n, which forms a group with respect to this product of subsets, that is called the quotient group. Most precisely, that is called the quotient of the group G by the normal subgroup n. Okay, so the quotient group, this G slash n, this is read as G mod n. Okay, so do not call it G by n or G divided by n or G over n. This is customary to call it, or this is standard practice to call it G mod n, or maybe G modulo n. Okay, yeah. So if we start with the normal subgroup n of a group G, then G modulo n is called the quotient group of G by n, and this is a group having the set of cosets of n as its underlying set and the product of subsets as its composition law. Okay, and of course, I mean this is indeed a group as we have just seen a while ago here. Okay, then we end this lecture by through a remark, by making a remark. It says that if you take an integer n, then this set nz, we know that it forms a subgroup of z. Moreover, we know that it forms a normal subgroup of z. Why? Because this ambient group z is abelian. Okay, and the group z mod nz that we have defined earlier is equal to the quotient group z mod nz. Okay, so why I'm making this remark? Of course, for two reasons. One is that this is to tell you that we have already met this notion of quotient groups, at least in certain specific cases, and that there is a room for confusion, because z mod nz can be treated from several, at least from two different, can be treated in two different ways. So first of all, z mod nz, okay, as we learned, okay, and another way is that this is a quotient group. Okay, so it was necessary to compare these two. Okay, and this remark says that they are exactly the same. Okay, so there is no room for confusion, and then we conclude with this notion of quotient group that we have just defined. We will be studying this notion up to some extent in this course. Okay, let me conclude.